The water supply for a hydroelectric dam is a reservoir with a large surface area, right? That means, by the way, if water is flowing out of here, we can say that essentially the velocity right there is 0. Okay, that's what the large surface area does. An outlet pipe takes the water to a turbine. State the difference in terms of velocity of the water between laminar and turbulent flow. Okay. And basically, remember that turbulent flow is this notion that as it flows down the pipe, the velocity is very chaotic and random, right? Laminar flow, anywhere in the pipe, right, the velocity is going to be more or less the same, okay? So to talk about that, right? Then it says the water level is at a height h above the turbine, right? Assume that the flow is laminar in the outlet pipe, right? Show using the Bernoulli equation that the speed of the water as it enters the turbine is given by, this is basically Torricelli's theorem, right? So let's say that this is situation 1. This is situation 2, right? So we have P1 plus rho G H1, right? Which H1 is just H, right? Plus 1/2 rho V1 squared is equal to P2, that's the pressure down here, right? Plus rho GH2 plus 1/2 rho V2 squared, right? Okay. Now, pressure 1 and pressure 2, the pressure exerted on the fluid on the outside is atmospheric pressure. There's very little difference in atmospheric pressure. So P1 equals P2. So those are going to drop out of the equation, right? We can say that H2 is 0. Okay, so that's going to drop out. So now you've gotten rid of this rho GH term, right? You've gotten rid of this guy because these two pressures are equal, right? Okay. And then on this side, on the left side here in the reservoir, we can say that the velocity at 1 is 0. Okay. And you'll end up with rho GH1, substitute the H in for that. Big H, big H. That equals 1/2 rho V2 squared. And V2 is, of course, just the V that they have there. Okay. Set those guys equal, solve for V, and you should be good. Okay. And then we get to the Reynolds number, right? Reynolds. And, you know, I feel like the Reynolds number is, in the data packet, is density times, all these are all inertial things on the top, right? Divided by the viscous stuff on the bottom, the viscosity on the bottom, right? Okay. I feel like pretty clearly in the data packet it says that that thing is an R, right? It's the radius. I'm just going to check this because I'm pretty sure of that. Okay. Because see, here's the funny thing is that the mark scheme uses the diameter, which is sort of funny. And then they say allow allow use of the radius. It's like, I think you're supposed to use the radius. Okay. But anyway, just plug and chug, baby. Here's your here's your velocity, right? I use the radius because it says radius. You know, I'm not very smart about this stuff, but there it is, right? There's your density, right? Yeah. I love this question. It's like, plug those numbers in, right? You're going to get a huge number. It's a gigantic Reynolds number, okay? And then outline whether it is reasonable to assume the flow is laminar in this situation. Well, remember that Reynolds number is bigger than 1,000, imply that there's perhaps a bit of turbulence. Certainly ones that are on the order of tens of millions would talk about, would speak for quite a bit of turbulence, right? So anyway, when you look at the mark scheme, realize that they actually use the diameter. I just don't know why, okay? Instead of the radius of this thing, you know? I don't know. I think it's kind of a loosey-goosey sort of thing, but then, you know, there you go.